Okay, here is part 2 of the chain rule for partial derivatives. Just as a reminder, in part 1, what we had was, so this is just a reminder. We had the function z, which was a function of two variables, x and y, and these two were both functions of t. And to find the derivative of z with respect to t, we had the partial derivative of z with respect to x times the derivative of x with respect to t plus partial derivative of z with respect to y times dy over dt. Okay, here in this lesson, we go a little bit further, and suppose z is a function of x and y, and x and y are not just functions of t, they are functions of two variables, s and t. So y is also functions of s and t. Now let's see what will be the chain rule in this case, that z is a function of x and y are function of s and t. The chain rule that we discussed before was when x and y were just functions of t, but here x and y are functions of s and t. Now at the first level, z is a function of x and y, but in the second level, z is a function of s and t, So it doesn't make sense to say that dz over ds or dt, because at that level, I have two variables, s and t. So the chain rule in this case will be as follows. For the partial derivative of z with respect to s, let's see how we can find this. To get from z to s, I can get through x, this path, and this path tells me partial of z with respect to x times partial derivative of x with respect to s. Pay attention that x is of two variables. That's why I use the partial derivative notation for x with respect to s. But that's not the only way to get to s. I can get to s through y. Through y, I have this path. So that I should add this to partial derivative of z with respect to y times partial derivative of y with respect to s. Likewise, if I want to find partial derivative of z with respect to t, I should follow the paths that reach t. So let me erase these two. Now I want to get to t through x. The path that goes to t is this path. So partial derivative of z with respect to t is equal to partial derivative of z with respect to x times partial derivative of x with respect to t. The other way to get to t is through y. This is the path. So actually, this should be added to the product of partial derivative of z with respect to y times partial derivative of y with respect to t. So these two form the chain rule for the situation that you see its tree diagram here. Now let's see an example. Okay, let's see an example here. In this example, z is xy plus y squared, and x as a function of s and t, it is 7s. X is 7x, I'm sorry, 7s plus 2t, and y is minus s plus 4t. So part one of this problem is to find a partial derivative of z with respect to s. Or the other notation as we have seen before when I introduced the partial derivatives, I can use z with an index s. They have the same meaning. I'm sorry, let me make this correction. Partial derivative of z with respect to s, sorry. So the first part, I want to find partial derivative of z with respect to s, or the other notation is z with index s. So I want to post my answer here. So based on the chain rule, this is going to be equal to partial derivative of z with respect to x times partial derivative of x with respect to s plus partial derivative of z with respect to y times partial derivative of y with respect to s. Okay, partial derivative of z with respect to x. Here I should look at y as a constant. Partial derivative of z with respect to x is just y. Partial derivative of x with respect to s, I should deal with t as a constant. That's just 7. Then plus partial derivative of z with respect to y, I should deal with x as a constant. So it becomes x plus 2y. And partial derivative of y with respect to s, I should deal with t as a constant, and partial derivative of minus s. I'm sorry, partial derivative of y with respect to s. Minus s is like minus 1 times s, so that's partial derivative is negative. Okay, so here we have 7y, and that negative is distributed over the parentheses. It becomes minus x minus 2y. 7y minus 2y is 5y, and then minus x. Again, we need to go back to the original variables, s and t. What is y? Y is minus s plus 4t. And then minus x. What is x? It is 7s plus 2t. Now, if you distribute 5 over the parentheses and distribute the negative over the other parentheses and simplify, you will get minus 12s plus 18t. So the answer is minus 12s plus 18t. Okay, now we do the second part of this example. The second part is to find zt, or partial derivative of z with respect to t. Again, you can pause and try this on your own and then look at the solution. Using the chain rule, this is going to be partial derivative of z with respect to x times partial derivative of x with respect to t plus partial derivative of z with respect to y times partial derivative of y with respect to t. Okay, as we know, z is xy plus y squared. The partial derivative of z with respect to x is just y. Now let's find partial derivative of x with respect to t. X is 7s plus 2t, so the partial derivative with respect to t is 2. Then partial derivative of z with respect to y, z is xy plus y squared. Partial derivative with respect to y is x plus 2y. And then times partial derivative of y with respect to t. Y is minus s plus 4t. Partial derivative with respect to t is just 4. Now let's simplify this. This is 2y. The other one, 4 is distributed over these parentheses. 4x plus 8y, which is 10y plus 4x. The final answer should be in terms of s and t. I know that y is minus s plus 4t. Four times. And x is 7s plus 2t. Which is after distributing the numbers over the parentheses and combining like terms, at the end, what we get is 18s plus 48t. So that's the final answer here, 18s plus 48t. Let's do another example. The next example has just one part. The function in terms of x and y is w. So let's w be equal to e to the power of 2x plus 3y. So the power of this exponential function is 2x plus 3y. So e to the power of 2x plus 3y. And I know that x is given as s times t, and y is given as y is s plus t. The only part of this question is find partial derivative of w with respect to t. So please try this on your own before watching my solution. So using the chain rule, this equals partial derivative of w with respect to x times partial derivative of w with respect to t plus partial derivative of w with respect to y times partial derivative of w with respect to t. Now we need to find each of these components. Partial derivative of w with respect to x. I should look at y as a constant using the chain rule in the sense of calculus 1 that we have learned. You know from calculus 1, the derivative of e to the power of 2x plus 3y with respect to x, dealing with y as a constant, is 2 times e to the power of 2x plus 3y. The chain rule that we use for this part is just calculus 1 chain rule. The derivative of, here on the top, there was a mistake here. It was partial of x with respect to t. Now, partial of x with respect to t, I should deal with s as a constant. X is st. Partial with respect to t is just s. Then plus partial derivative of w with respect to y. Now I should deal with y as a variable and x as a constant. And the derivative is going to be 3e to the power of 2x plus 3y. And partial derivative of y with respect to t, y is s plus t. The partial derivative with respect to t is just 1. So let's simplify, and finally we need to write everything in terms of s and t. So 2s e to the power of 2x plus 3y plus 3 times e to the power of 2x plus 3y. So what I should write inside this box, I need to replace x by st and y by s plus t. The final answer in terms of s and t is going to be 2s e to the power of 2x, which is 2st, plus 3y. Y is s plus t, so 3s plus 3t. So all of 2st plus 3s plus 3t is the exponent of that exponential part. Plus 3 times e to the power of 2x plus 3y, the same thing, 2st plus 3s plus 3y.